how the matter is arranged. So matter comes in, predominantly three forms. Okay, you could think of it like that. So essentially, you can have a perfect regular arrangement of silicon atoms, okay, which we will call as crystalline state, in which the interatomic distances are exactly fixed. Okay, so you can have this perfect regular order, which is perfect order. Okay, this is basically important. We call it as crystalline state. In another state, you could have a situation where there is no order. Okay, basically there is no long range order. We'll say. Okay, basically there is, there is not even short range order here actually. So the atoms are randomly distributed, and this is called as amorphous state. Okay? And then we have a third state, which we'll call as polycrystalline state, wherein you have small domains. Okay, so these domains, in each pattern, right? Domain having short range order. Short range order. That means the relation between atoms is fixed, that the distances are fixed perfectly. Then it's a short range. You have a short range domain, but then if you go to long ranges, there is no order. They're all randomly aligned. So that is called as polycrystalline. It's consisting of many, many small crystals. So this is a polycrystalline state. And it makes a big difference whether, material is in which state, right? So for example, silicon that we use in our electronic devices is always in the crystalline state. We like the crystalline state most. Okay. Sometimes we use polycrystalline silicon, but that we will talk about later. But we like crystalline state so much so that it is a very, very highly pure form of silicon. We will take in our electronic devices silicon which is 99.9999 times basically pure. This is a percentage of purity. If you look at 1 billion atoms, there might be one single impurity in that. That is the level of perfection, perfect purity we use for our electronic devices. All right. So fine, you have these states, but how are they arranged? That makes a big difference. Okay. If you look at silicon, it forms what is known as a diamond lattice. A diamond lattice is simply represented here. So you have a cube, and in the cube, you have silicon atoms which are present. For example, you have 8 silicon atoms at the corners here, right? So in the corners of the cube, you have 8 silicon atoms, and then you have 6 silicon atoms at the faces of the center of the face. Like a cube has 6 faces, so side, top, bottom, and so on. So you have 6 faces. In the center of each of those faces, you have a silicon atom. And then there are 4 atoms which are in the interior, in the diagonal, along the diagonals of the unit cell. Okay, this particular thing is called as a unit cell. And this length is basically called as lattice constant, which is equal to 5.43 angstroms as given here, right? So this is a lattice constant. So this is how silicon atoms are arranged in a crystal. Okay. So this makes a big difference for us. Okay. And one important point you should note is that every silicon atom is actually connected to 4 nearest neighbors. Okay, think about it. If you look at one silicon atom here, it's connected to 4 atoms. And this atom also is connected to 4 atoms. The ones which are in the corners, they're also connected to 4 atoms, but from the neighboring unit cells. One already, there is one connection here, and then there is one connection here, one connection here. There will be another from the neighboring atom, neighboring unit cell. So that will have 4 connections. Okay. So there are exactly 4 nearest neighbors for each silicon atom. And you could actually compute, what is the density of silicon here. Okay, it's not very difficult. I'll maybe put it in the homework. But basically, it turns out that the density of atoms in silicon is about 10 power 5 into 10 power 22 atoms per centimeter cube. Okay? I want you to keep this in the back of your mind. Okay? This is a very important number because when we talk of doping in silicon, we have to use this as a reference. Okay? So basically, it tells you that if you have 1 centimeter cube of silicon, it has 10 power 22 atoms. Right? It's a very, very large number of atoms. Okay? And this is going to play some role. And finally, the electronic properties are going to depend on what is the phase of your silicon. For example, if you have a crystal, what we said is you have this unit cell, which is actually having these atoms. And now, if you take a bulk piece of silicon, it is essentially consisting of these unit cells, which are arranged in this form, right? In 3 dimensions. So basically, this exact unit cell will repeat many millions and millions of times. That is essentially a crystal. So you have exactly the same distances. It's like, you build a Lego block or something, right? Essentially that. So these unit cells are built, in 3 dimensions. So it becomes important. What is the arrangement of atoms in the top of silicon? If you take a top surface of the silicon, bulk silicon, it becomes important. For example, is the arrangement of atoms in this fashion, wherein you have four atoms in the corners and then center, one atom. Is that the orientation, or is it the orientation this way along the diagonal? Okay, you have many more atoms along the diagonals, right? So it becomes important, and there's a lot of in the textbooks, if you look at it, they'll talk of what is known as Miller indices, okay, to denote what is the crystal orientation. And I really think that that is not really that important for us. So I just not going to talk about it much. It's there in your textbooks. If you are interested, you can actually do a little bit more of study, but I don't think it is that important for the purposes of this course. Okay, it is something that you can study. Okay, so essentially this Miller indices define, and we are not going to get into that. But what we would like to understand is, how do you think of energy levels when there are atoms close to each other like this? When you have a silicon which has four atoms close to it, how do you think about the energy levels? Okay, that's something we need to understand. And to do that, we'll actually simplify, because it's not very easy for us to think of this diamond lattice all the time, right? It's somewhat complicated. So what we do is we represent, this is basically a two-dimensional visualization. Okay, visualization. This is not really the accurate picture. So if you want to accurately think about it, each silicon atom is connected in 3 dimensions, right? Like tetrahedral. The corners of a tetrahedron are silicon atoms, and the center is what you have, right? So it's difficult to think about it. So what we'll do is we'll represent in a 2D picture like this. So what we are doing here is, each of this is basically a silicon atom. Okay, and it is connected to 4 silicon atoms. For example, this, if you take this silicon atom, it is connected to 1, 2, 3, and 4 silicon atoms on the 4 sides, right? So this is, again, it's sort of a representation of what is happening. Okay, and what did we see? We saw that silicon atom has, in the outermost shell, 4 electrons. Okay, there are 8 available states, but 4 electrons, and that is not really a stable form. We know from our basic chemistry that the atom always tries to have the fully filled shell. That is a more stable form, right? That's why argon is very stable, right? So silicon also tries to get 8 electrons in the outermost shell. How does it achieve that? So if you want to represent, I can maybe represent, like, I can put a minus here to denote electron. There are 4 electrons in this silicon, okay? But it has 8 states. How does it get 4 more electrons? Well, it shares with the neighbor. So this guy has a 4 electron. This guy has this guy has 1 electron, 1 electron, 1 electron. So these 4 electrons from the neighbors are shared, and they form a covalent bond. Okay, and the covalent bond is represented in this picture by these lines. Okay, these lines are representing your covalent bond. Okay, so once this covalent bond happens, because of the sharing, you see that each atom of silicon has 8 electrons. For example, if you count here, there are 2 lines here, there are 2 lines here, 2 lines here, 2 lines here. So each atom of silicon has 8 electrons, so it is in a stable situation, stable configuration. Okay, so this is a simple 2D visualization. It is not exact picture. Exact picture, you have to talk about the diamond lattice. But for us, later on we will try to remove one silicon and put something else, that we call as doping. And then what happens if you actually break one of these bonds, right? Because, let's say this bond is broken. What does it mean? If the bond breaks, that means your electron can go somewhere else. It's not bound to the lattice, but it can freely move about. Okay, so this is again an important thing. We will talk about it in the next lecture. But for now, let us complete the understanding of how to get energy bands. Okay, so now we understood individual silicon atoms, right? We said that, okay, there is these discrete energy levels which are formed, and then you can call it 1s, 2s, and so on, and all that. That is fine. But what happens when I bring 2 silicon atoms close to each other? Is it the same thing? Okay, it turns out that, well, it's not that simple. But before I get into those details, I would like to tell you how a silicon lattice can be represented. Okay, so we already saw this, when we said that each silicon atom has a potential of the form 1 over R. Okay, so this is 1 over R, and then you have silicon atoms which are arranged in an arrangement, right? Some arrangement basically. It could be some distances depending on the phase of the, which phase we are talking about. There will be different arrangements, but in effect you have a perfect order, right? This distances are known to you. Okay, so you have these atoms, each of which is essentially a potential well, and all of them are essentially next to each other. When you have such a scenario, what happens is these are very strong potentials, but then because of the interactions, the effective potential becomes like this. Effective potential due to silicon atoms, right? Neighboring silicon atoms, you have this. So this is sort of similar to basically a series of potential wells. Okay, for example, here this region 2 basically is a barrier, right? Region 1 is basically a potential well. Okay, so what we are saying is, of course, this is the real situation, real, how the potential will look like. But if you want to solve this, it's going to be very, very tedious, and you have to do it using a computer. You can't do it manually. Okay, so we approximate, okay, we approximate this real potential using basically a series of barriers and wells, and this we call as chronic penny model. Okay, so you see the beauty. So we know how to solve a finite potential well, right? And now simply this is a series of potential wells. That's all. We have to solve for this. If you're able to solve for this, we can predict how electron moves in a crystal. Okay. So even though seemingly complicated 1 over R dependence with millions of atoms, that kind of can get reduced to this. Okay. So again, this is solved in your textbook, but I don't think it is essential for you to right now look at how the problem is solved. We'll just tell you the conclusions of what it is. Okay, what happens after the chronic penny model. But I'll try to give you an intuitive picture in the next 5 minutes or so. All right. So for the purposes, I would like to understand how the origin is happening. You should be intuitively convinced about what we are doing. That's all I want you to do. Okay. You don't have to remember these things, but you just have to be clear how the thought is flowing from infinite potential well to finite potential well, and then a series of potential wells. Right. That's the flow of thought here. All right. So now we have this series of potential wells, but how do we understand what happens in this series of potential wells? To do that, we will take a simple scenario. Okay, consider a finite potential well. Okay, I'm only showing you this. This is a finite potential well with let's say some depth. Okay, it's not important for right now, and I'm only showing you one particular state. It can have many states, right? But I'm showing the ground state, the first state. So you saw that the potential basically has some sort of a you will have maximum probability of finding an electron in the well, but then there is some small leakage of wave function into the barrier regions, right? This is what we saw. Let's call this wave function as psi a. Okay, this is for one potential well, and now let's think of another potential well, another atom essentially, which is at some distance away from this. Okay, so let's call this as psi b. It has a wave function also, right? And because we are talking about the same atom in the same environment, if they're far apart, right? When this, distance is large, right? And let's call this distance as d, okay? When d is large, okay? Few microns, let's take it. There's no harm, right? When d is large, it should be that psi a should be equal to psi b. Right? There's nothing else, right? It has to be, similar potential, similar, everything. So it has to be a similar wave function, right? So that means what is the energy? If you want to call as E1, energy of the first potential well, and then E1, let's put a superscript A, okay? Just to denote that it is energy level of the first well, and then you have energy level E1 of the second well. What will be the energies? What will be the relation between these two energies? Well, because they are very far apart, these energies are going to be equal. Okay, so we will call this as basically degenerate energy levels. Okay, now if you have 3 potential wells, what happens? Well, you will have 3 degenerate levels. If you have 4 potential wells, if you have, you'll have 4 degenerate levels. And if you have n potential wells, implies you have n degenerate energy levels, okay? Well, I'm only showing you one particular state, right? E1, right? That's, you can have similar things for E2, E3, and so on. Each of these energy levels will be n-fold degeneracy. Okay, we'll have n-fold degeneracy. That's the term we use. Okay, technically. All right. So far, so good. But what happens if I start reducing the distance d? Okay, when I reduce the distance d, when d reduces, there is interaction, right? There is interaction of wave functions, isn't it? Because these are finite potential wells, there is some penetration of the wave function into the barrier region, and then as you bring these two things closer, there'll be more and more interaction, right? So what happens because of that? Well, to understand that, we have to think about what is the most important thing in the practical world. The probability of finding an electron is important. Okay, so since we said this was psi a, right? This is psi a. So psi a has a probability of psi mod psi a square. Will minus psi a satisfy? If I consider minus psi a, will it satisfy the Schrodinger equation? Of course it will, right? So what happens is, when you start having these two potential wells, the overall wave function is going to be a superposition of individual wave functions. Okay, there will be a linear combination of wave functions. So I'll say my overall wave function psi is going to be C1 times psi A plus C2 times psi B. This is a linear combination of wave functions. Okay. Now what can happen is, you can have a situation where both these wave functions are positive. Okay. So I can have a situation where this is, I'll say this is positive and this is positive. Okay, that is one solution that is allowed. You can also have a situation where this is negative and this is positive and this is negative. Okay, you can have other combinations as well. Well, right now let us just stick to these two states. Okay, so when you have these two combinations, you'll have wave functions which turn out to be in the form that is shown. The green one, we will call it a symmetric wave function. Symmetric. I mean, this is additional detail. I mean, it's not really necessary for you right now, but anti-symmetric wave function. So as the d reduces, the probability, if your d is large, the probability, let me call it psi symmetric and psi anti-symmetric. Okay, let's call it these two functions. The shapes are different, right? When d is large, the probability of psi symmetric square, right? I mean, the probability of finding an electron in this way is equal to psi anti-symmetric. There is no difference when d is large. Okay, but when you have the distance reducing, then they'll start interacting and the probability will slightly be different. Okay, because of which you will have two energy levels which are having a small difference in energy. Okay, so this I'm running out of space here, so I'll just show the energy levels here. Okay, I'll call this as delta E. So what we're saying is, as D reduces, delta E increases. Okay, there is more and more difference. As you bring the wave functions closer, there is more interaction, because of which the probability psi symmetric mod square is not equal to psi symmetric psi anti-symmetric, right? So I can say the energy levels are basically delta E is basically E anti-symmetric minus E symmetric. Okay, so as D reduces, delta E increases. Okay, so this is what physically you would expect it to happen. Okay. So one level essentially has become two non-degenerate levels. Okay. So in the first situation, let me try to add a page here. Okay, so let me zoom it in this way. So in the first situation, right, you had independent or non-interacting. That's a better word. Okay, non-interacting potentials. Non-interacting potential wells. When you have non-interacting potential wells, you have basically delta E is equal to 0. I mean, there is no difference in energies. So basically, you have if you have n potential wells, right? N potential wells, n wells imply n degenerate levels. Okay. So basically, the energies are all same. They have the same energy level. Okay. But if you have interacting potential wells, then if your interaction is strong, right, the interaction is basically given by what is d, the distance, right, the well spacing, right. If your well spacing d reduces, that is more implies more interaction, right, more interaction. Sorry, interaction. If interaction is more, then delta E, which is simply E antisymmetric minus E symmetric, is going to increase. Delta E is going to increase. That means instead of having, in this case, you had single energy levels, right? In this case, you'll end up getting, sorry, I should actually draw it on the same line. Okay, there are two levels basically. This is a level energy n-fold degenerate. In this case, you would see that energy levels are, there is a small lifting of degeneracy. Okay, this is your delta E. Okay, due to basically now you don't have degeneracy. Basically, degeneracy lifted due to interactions. All right. So what happens if you have n atoms or n potential wells which are coming close to each other? You will have, in the non-interacting case, you have n-fold degeneracy, but in the interacting case, you will end up getting n levels closely spaced. Okay, that's what happens. All right. So no, it's okay if you're, I'm sure that you will not understand it fully in the first time. Please revisit it. And if you have any questions, we will try to have a interaction one-to-one. You please schedule a interaction whenever the course is running in July. So we will discuss it in greater detail. Okay. So don't be confused if you are, don't be upset if you are not understanding in the first time. I'm actually taking a little bit more of, giving a little bit more of details to actually fill the intuitive picture. Okay. So, well, yeah, it will take you some time to understand. Maybe even the first offering of the course, it will not be clear, but later, if you see it, if you do research in electronic devices later on and you come back, I'm sure you'll find this, very, very important. Okay. All right. So let's come back. So this is essentially, that's the intuitive picture of what is happening. I just, went one more step ahead, and then actually we calculated these things using the software, and we are showing the results. Okay. So when your D is large, we said that, there are two wells and the probabilities are looking like this. Okay. But, as you, if you increase the distance, sorry, if you decrease the distance, right? This is the decreasing distance. As you decrease it, you will see that the energy levels are actually having small gaps. Okay. So this is represented by delta E here. So in the lowest energy level, it was 0. In the second level, it is 0.01. Very, very small gap in the difference in the energies. And here it is 0.08. But the moment you actually make it very close to each other, you see that there is significant amount of different splitting between the levels. Okay. This is just just if you're curious, it is just an additional thing, but it actually happens. It's not just hand waving. It actually happens if you calculate it fully numerically accurately. You will see this. Okay.